Let's look at force field in this video. In physics, we have two types of forces. The first one is the contact field, in which they are in contact with the forces they act on. While the second type of force is the force field. Force field are forces which act on a body without direct contact, e.g., gravitational field, electric field, and magnetic field. So in this video, we want to study what the gravitational field. What is the gravitational field? It is a region or space around a mass where gravitational force can be felt. So let's look at the Newton's law of universal gravitation, which states that the force of attraction between two bodies in the universe is directly proportional to the product of their masses. Assuming the two masses are m1 and m2, is directly proportional to the product of their masses, m1 plus times m2, and inversely proportional to the square of the distance between them. Take a look. Assuming this is a body, m1, and I have another body, m2. Now, if this is the distance between them, assuming this point like this is the distance between them and its distance r, for example, so the force of attraction is inversely proportional to the square of the distance between them. The distance is r, so it's square of what? R. So that is it. So this is the statement of the what? Of the Newton's what? Universal law of what? Of gravitation. So that is the statement. So let's go ahead. When a variation sign should change to equal to, you know that what? The formula will now be F is equal to, now you introduce a constant. The constant is what? G. Then m1, m2 all over r square. Good. This is the one we normally use to solve. Exactly. What is G? G is the gravitational constant, and it has a value of G equal 6.67 times 10 raised to power minus 11 Newton meter square per kilogram square. This is a constant. So that is it. Always take note that, let me assume that, assuming m1 is equals to m2, what happens if the masses are equal? Then m1 will be equals to what? M2 will be equals to what? M. Therefore, the formula will now become F equal to G. This M will now become M times M, and M times M will give me what? M square all over R square. This is the cases when the masses are what? Are equal. Note again that what? All force field always what? Always obey the inverse square law. We call this the what? Inverse square law. Now, what is the inverse square law? The inverse square law have to do with something like this. When we consider only the force and the distance between them. Let's see. If I consider it, I will have what? F to be what? Inversely proportional to the what? To the square of the distance between them. Let me erase this part. Then after that, I'll say F is inversely proportional, or let me say I introduce equal to, and I have a constant k all over r square. So therefore, if I cross multiply here, my k will be equal to what? Fr square. Listen attentively here. If a particular quantity is kept constant, then I can say F1 R1 square equal to what? F2 R2 square. Now look at this statement. This is the statement of the what? Of the inverse square law. How do we use this inverse square law? Anytime they are giving you questions on the force of attraction between them and the distance between them only, if they did not mention the mass in the question, they are not making reference to when the distance between them was something, the force was something. Now, what will be the force when distance is this? Note that the question is having to do with what? The force and the distance only. So you are using the word, the inverse square law. That's that. Now, let's go back to the Newton's law of universal gravitation, which states that The force of attraction between two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. If you look at this relationship here between this one and this one, they are inversely proportional. It means that if you say inverse relation, it means that when one increase, the other will decrease. It means something that if they are far apart from each other, this one will be what greater, it will be large. And once this one is large, the force will be what? Small. Are you there? That's the meaning of inverse square law. When one is large, the other will be small. When one is small, the other will be large. Now, if I bring the two masses close to each other, what happens? This will be what? Small. Then the force of attraction will be what? Will be large. So that is it on Newton's law of universal gravitation. Furthermore, a body that is revolving around the Earth is kept on its orbit by two opposite forces. Again, two body that is revolving around the Earth is kept in its orbit by two opposite forces. What are those forces? The centripetal force and the centrifugal force. The word centripetal force means the force that always acts towards the center. The word centrifugal force is the force that always acts away from the center. So these two forces balance each other. Therefore, the body can be able to revolve around the Earth without falling. So that's that for that. Let's discuss the weight of an object in this video. What's the weight of an object? See, the weight of an object on the Earth is due to the gravitational effect of the Earth on the body, while the weight of an object on the moon is due to the gravitational effect of the moon on the object. And the weight of an object, W, is equal to the mass of the object times the acceleration due to gravity. And the weight of an object, we measure it in in newtons. This is the unit, newtons. That's it. Now, when an object exists at an infinite distance away from the Earth, what happens? The object feel what we call weightlessness. Exactly. When an object becomes weightless, it means that it has exist at a very great distance away from the Earth. So therefore, as you move far away from the Earth, what happens? This acceleration due to gravity tends to zero. Then at that point, your W, the weight of the body, will become zero. And this is what we call the weightlessness. So that is that. So what are the factors that affect the weight of a body, or what are the factors that affect acceleration due to gravity? Now let's explain those factors. The first factor is the shape of the Earth. So note that the Earth is not perfectly spherical, and because it has some bulges at the surface and likes. Now note that the acceleration due to gravity on the Earth, let me say this way. The acceleration due to gravity at the pole, of the Earth is greater than the acceleration due to gravity at the equator. Note that. Why at the equator? Why? Note that as the Earth is not perfectly spherical, then r, the radius, varies along the Earth's surface. Note that this r that vary along the Earth's surface is greater at the equator than the pole. And I want you to note something. That we also know that the weight of a body is inversely proportional to the square of its distance. Remember when I discuss inverse square law like this, the force and the weight is same, okay, because the weights have to do with force of attraction. So you see that from this formula you can see that the weight here is mg. You can see that the g and the r here, they are inversely proportional. It means that anytime the radius increase here, the acceleration due to gravity will decrease, and anytime this one decrease, the acceleration due to gravity will increase. Now look at this relationship here. Look at this relationship. You can see that what r is greater at the equator than the pole. Are you there? Then this one will be opposite. G is greater at the pole than the equator. So this means that an object will weigh more at the pole than the equator. So that's the first factor that affects the weight of the body. So another factor is the variation in altitude. Or you can say the variation in height of the body. Okay, remember I told us that as the object go far, the weight of the body will reduce. So also you can say variation in altitude, variation in latitude and longitude. Okay, so that's the other factor. The last factor is the rotation of the earth about its axis. So how does this affect the weight of an object? Now see, note this equation, that the force, the centripetal force, is equals to what? The force of attraction minus the weight of the object. So look at this. From here you can say this centripetal force is from the rotation of the body, and this is the force of attraction, the gravitational force of attraction, while this is the weight of the body. So you can see that the weight of the body can be affected by the rotation about its axis. So that's basically the three factors that can affect the weight of a body. So that's that for that. So if you have a body at different location of the earth, how does the weight vary? Remember I said that the weight of an object is equals to what? Mg. So assuming we have an object at a location, if you look at this now, you will see that the mass of the body is equals to the weight all over acceleration due to gravity. So at different location, I'll have the weight over g1 equals to the weight all over g2. Look at it. It means that at different location they'll have different g and different weights. So note that the mass of the body is always constant. The mass is always constant. If you are on the earth and you are on the moon, your mass will not change. Okay, it's always constant. Exactly, mass is always constant, but the weight depend on this, and this acceleration due to gravity is not the same thing along the earth surface. Remember, it's greater at the pole and smaller at the equator. So the mass here does not change. It does not depend on anything, so it doesn't change. So on the earth, on the moon, you have the same mass, but on the earth and moon, your weight varies. So that's that. Let's look at the acceleration due to gravity in another aspect. We all know that from Newton's law of universal gravitation, we all know that the force of attraction is equals to G. If I'm considering two masses here now, let this capital letter M be the mass of the earth, let the small letter m be the mass of the body, then all over r square. Now from here, if let me use this one as capital letter R, but no problem. Now let me consider the force to be the weight of of this body here. Then my force will be equal to mg equals to g m all over r square. From here, the small m will cancel the small m, so I have the g to be equal to capital letter g m all over r square. Now note this formula. This one have to do with the relationship between g and capital letter G. Remember, this small letter g is the acceleration due to gravity, while this capital letter G is the gravitational constant. So this is the relationship between them. So m is the mass of the earth, again is the mass of the earth, while this g is the distance between the object and the and the earth. So that's it. Now that's that. So assuming this r is the radius of the earth. Okay, is the radius of the earth. Good. This is the mass of the earth. Mass of the earth. Good. Now, this is when the body exists in the earth. Now, consider this picture. Consider this picture, and assuming this is my earth, for example. Assuming this is the earth, and then the radius of the earth is from here to here. Let me say r. I'm coming. If this is the earth, for example, and then the radius of the earth, let me say like this, and is r. Let me take for instance that the body is not in the earth's surface. Assuming the body is at a distance, let me say it's at a distance h from the earth's surface. Now this one is another case. Let me say this is the object. Now you can see the object is not within the earth, it's at another distance away from the earth. So what do we do in this case? Now you will see that this formula will just change a bit. It will now become, you know, this g that is here is the gravity that will occur on the earth's surface, but at the height here, let me say the acceleration there is g prime. You know there will be different g because they are on different location. Now let's move. So this g at different location will be equal to what? Gm all over. You know that this r was when is on the earth's surface like this. Now the object is now at a distance h above the earth's surface. It means that what? The distance will now be from the object to this point is h. From this h to the center of the earth is what? Is r. So the total distance from here to here will be what? R plus h, or h plus r. So I will now have what? So instead of me writing r square only, I'll replace r square with what? R plus h all square. So this is the gravitational, this is acceleration due to gravity at a point above the earth surface, above, like at a distance r from the earth's surface. So let me take for instance that this is the earth again, and the radius of the earth is what? Is r. If the object is at a distance r away from the earth, what will be the total distance to the center of the earth? It will be what? R plus r, which is what? 2r. So your formula here will be what? Gm all over r plus, what is your h? H will now be what? H will now be what? 2r then square. So that is it. So note this formula. Now let's go ahead. Look at this. Look at these two formula. Let me call this equation 1 and let me call this equation what? 2. So if I say equation 1 divided by equation 2, what will I have? I will have g prime divided by g equal to gm all over r plus h all square divided by gm all over r square. If you see, you see that I'm dividing this one by this one. If you see, good, let's move. So from here I'll be having what? G prime over g equal to gm all over r plus h all square times r square all over what? Gm. This will take care of this. Then I'll be having g prime over g equals to what? R square all over r plus h square. If you observe, this numerator is far less than the denominator. This is very clear. This one will be less than this one. So you know that if the numerator is smaller than the denominator, for example, if I have 3 over 5, you know this value will always be less than 1, right? Good. So it means that since this numerator is smaller than the denominator, therefore g prime over g will be less than 1. Note that the acceleration due to gravity will be less than that. So if I cross multiply this here, I'll have g prime less than g. You can see the acceleration due to gravity at a point above the earth's surface will be less than the acceleration due to gravity on the what? On the earth. So can you see that? So note that. So, and note this fact again, that gravitational acceleration due to gravity on the moon is equal to 1 all over 6 acceleration due to gravity on the what? On the earth's surface. Okay, so it means that what? An object will weigh less on the moon than the earth. So that's why astronauts, when they travel to the space, you see that what? They will be floating if they are not on their heavy jacket and their cylinder. Okay, because they will be weightless. And you see the way they walk on the moon, they drag their feet on the moon. They don't carry it because they are weightless. Okay, so that's that about that on this video. Gravitational field intensity. So the gravitational field intensity, e.g., we call it gravitational field intensity. So the gravitational field intensity, EG, is equal to the force per unit what? Per unit mass of the body. Now, let's look at something, guys. What is the formula for this force here? Due to Newton's law of universal gravitation, is what? G m all over r square, then divided by this, like I'll bring it a denominator like this. So this will take care of what? Of this. So the formula for the gravitational field intensity is equals to what? Gm all over r square. So take note of the formula this way. And I want you to note that the gravitational field intensity is equal to the acceleration due to gravity. Don't forget, let me prove that. You know, F can be equal to mg if you consider the weight of the body. If I make the mass subject of the formula, we're having m equal to what? F over g. If I make the g subject of the formula, we're having g equal to what? F over m. Now look at this, and look at this. You can see that what? G and EG are the same thing. So note that, don't forget. So that's what they call the gravitational field intensity. Okay, so that's the formula. Jot it down. The next one, we'll be looking at the gravitational field in the gravitational potential. The gravitational So let's look at gravitational potential. Gravitational potential is denoted as what? As V. Gravitational potential is defined as the work done in taking a unit mass from infinity to a point. So the definition is what? In taking a unit mass m, from where? From infinity to a point. So from infinity to a point r on the what? On the gravitational field. So the formula to calculate this is what? V equal what? Negative gm all over r. Note that this thing is negative just because the potential at zero. Note that the potential at infinity is equal to zero. The potential at infinity is equal to what? Zero. That is why this one take a negative. Let me show that mathematically. If I have V equals to gm all over change in r. So I'm having gm all over, the change in r will be the r in the infinity minus the r in the what? In the point. You know that I'm having two distance from infinity to a point. So yeah, let's see. You know that 1 divided by infinity here will actually give me 0, abi? So therefore the formula will now shrink to, focus closely, it's now shrink to gm all over, this one has changed to 0. So is 0 minus 1 over r will give me minus 1 over r. Gm times 1 minus 1 over r will still give me what? Minus gm over r. So look at it, minus gm all over r will still give me what? This. So this is taking negative just because the potential at infinity is equals to what? 0. So take note of this what? Of this formula. But when we are solving, we always neglect the minus sign and just say v equal to what? Gm all over r. Take note of another thing again. Now take note that my v is equals to gm over r, neglect the minus sign. Now if I multiply r at the numerator and denominator, I'll be having v equal to what? Gmr all over r square. Let me say I have something like gm all over r square. This r times r give me r square. Then let me put this out like this. Recall that this gm all over r square is equal to g. So therefore my v is equals to what? Is equal to gr. Exactly. This is another formula for gravitational potential. Is either use this or use this. Thanks for watching. So the next thing is to look at the gravitational potential energy. The gravitational potential energy and the kinetic energy. So what do we need to know about this? Note the formula that the potential energy in force field is what? Negative G mm all over R. That is it. That's the formula. That's the formula you need to take note of. But I want to deduce something. You know that my potential energy here can be equal to what? Negative Gm all over R times m, right? Remember, what is negative Gm all over R? That is the gravitational potential, which is what? V. So therefore my potential energy, gravitational potential energy, will be equal to what? Vm. So just take note of it. So you don't need to cram. Just understand one, you know the other. So what the gravitational kinetic energy? The gravitational kinetic energy, Ke, is equals to what? Is the same, is half of this one, that is just multiplied 2 here all over 2r, but this one doesn't have minus sign. Exactly. So what can I do here again? Remember, I can turn this formula to Gm all over R times m over 2. Remember, I can just bring this one, I can just plug out m over 2 and put it to one side. So I have something like this. So remember, what is Gm over R? Gm over R is what? Is V. So therefore my kinetic energy will be what? Vm all over 2. Can you see it? Exactly. So that's the gravitational potential energy and kinetic energy.